Okay, perfect. So the last thing that we need to do in chapter two, then, just to finish up chapter two so we can move on to more interesting chapters, move a little bit away from the theory that drives how we actually store our data in terms of a representational form into our systems, and we can start moving more into the actual like machine code on how our systems operate is to handle the alternate numerical format that we haven't discussed yet. So we spent a lot of time and effort talking about integral data sets. Talking about integral data sets, right? Those are our countable values where there is a discrete step between one unit to the next, right? So like, for instance, in our integer space, we move from 0, 1, 2, 3, 4, 5, 6. Very powerful arithmetic operations can be dealt with that. But one of the things that we lose with that type of those type of number sets is that you can't define the amount of space between two values in the set, right? Like one of the big awesome concepts that's given to us in terms of real numbers is that we can have definable sets of values that occur in between, infinitesimally between. And so that's the true value that floating points give to us. Now, I've said this before, and I'll restate this again. Mathematically, anything that's represented as a radix point, as a fractional number, as a floating point number, is always an approximation. This is just, it's ingrained mathematically. It's inherent to that representation. That's why when you go through discrete mathematics, and correct me if I'm wrong, you usually have to do the proof that 0.9999 repeating is equivalent to 1, right? Did everyone kind of step through that proof? And so the reason why that proof is so valuable isn't just to show you like mathematical trickery, right? It's to illustrate that in order for us to map our radix points numbers onto the integer sets, that has to be a necessary truth. Okay. So with that said, let's see how we can take this idea of our floating point numbers and start encapsulating those, start encoding those as a binary sequence as well. And so I'll also highlight, and this should be evident after the course of these slides, the reason why the default value of floating point numbers is the double and not float is because you always want the higher precision when you're talking about approximations. So recall that integers are 32 bits in terms of its encoding space. There are long integers. You could use the long data type and get a 64-bit int, but typically you don't need a number that size. So the default is four bits, 4 bytes. I'm sorry, 4 bytes. Whereas with floating point numbers, whatever the maximum encoding amount of bits you have. So in this historically, it was your doubles, your 8 bytes. That was always going to perform better. It's going to be more accurate than your 4 bytes. And we're going to see why that's the case and why that's important and why if you ever need to use a floating point number, you should always use doubles and not floats. Another thing is if you can ever model something in terms of integer values, you should. Never, if possible, use floating point values. I think we've probably talked about that already as well, right? And we used the movie Office Space as an example. Okay, anyway, let's get back to the actual clocks. Here you can see I give you the floating point representation, which is going to encode in the form of this. So here, our value of V, which is going to represent our floating point number, can be defined as this term X, which is going to be our significand, or what's called our mantissa, which is the part that holds the precision or magnitude of the number. And then here, we're going to take 2 to the power of y, and y is going to be the exponent, which scales the number by powers of 2 and determines its magnitude. So we have a base, and we're going to multiply that by a exponent on 2. We're going to see how that actually translates. But this is typically mathematically how we're going to model all of our floating point numbers. So one of the powerful things about our floating point numbers is they're very good for large numbers, and they're very good for small numbers, so numbers that are close to 0. And they're an approximation as well. So they approximate to real arithmetic. So we talked about the encoding scheme we use for our integral numbers, right? We had 2's complement form, and we had the unsigned form, the just traditional way of doing counting in binary. The scheme by which we encode our floating point numbers was defined by the IEEE. So this is going to be the IEEE representation that we'll go ahead and take a look at. And so one of the big things it's going to explore is the rounding issues, which can affect our representation. So we'll cover that a little bit more in detail in these slides. And again, the mathematical properties are going to be addition, multiplication, and relational operators. Okay, let's take a quick look at what a fractional binary number looks like in practice. So here we have a radix point. When used on a binary number, that would be called a binary point, not a decimal point. Decimal point implies that it's a decimal number. So if you were doing a fractional number and a hexadecimal value, that'd be your hexadecimal point. If you want the generic term for that, it's a radix point. So don't by default call it a decimal point. It's only accurate when you're talking about base 10 numbers. Okay, so we have our binary point. So suppose we have placed it here, right? So just like with base 10 math, it will be similar in base 2 math. You have a left-hand side of your binary point, and you have a right-hand side of the binary point. So the left-hand side will represent where you have magnitudes that are in front of your fractional, that adds to your magnitude. So like, for instance, this would be, so if we were to eliminate the right-hand side, our B0 here would be the equivalent of 1, if that was in the 1 space, right? This would be like 2, 4, so 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, all the way to whatever value you're encoding is, right? So the left-hand side works the exact same way. We've already learned how to go ahead and do our binary count. And it works as an analog to the way we do it in decimal math as well. So that means that the right-hand side should also work as an analog to the way we would do this in decimal-based math, right? But as opposed to being 1/10, 100th, 1,000th places, it would be the equivalent of like 2 to the -1 place. So like 1/2 or 1/4 or 1/8 or 1/16 or 1/32, right? So based off of where those units appear are going to depend on what the exponential 2 is. So does that much make sense? I mean, so far that's an analog. And correct me if I'm wrong, did you already cover it in this much detail in assembly, or is this effectively all new data? I don't know how far y'all go into the IEEE representation.
I believe we touched up on it, but we kind of brushed over it. Right now we're learning it in composition.
Yeah, okay. Oh, perfect. So you're actually learning it in... Okay, well, that's good to have a little overlap. Okay, so one way that we can go ahead and then represent is that our bits to the right, represent the fractional powers of our rational number. And so here we can see we can take the sigma summation on the right to be able to actually compute from, let's see here. This is J to, this is B to the minus j, right? We can sum from there all the way until we get to our I term. And then here, we can take whatever the binary value is at any given time and multiply it by 2 to the power of k. So does everyone see how this sigma summation term, this mathematical term, matches to this representation, this visual representation? Because if so, I want to go back towards our linear algebra definition here and say this states the same thing. It's just instead of sigma summation where we're showing the per element operation, right, using the sigma summation operation, this is a vector times a vector to produce another vector. This is the vectorized operation, which, side note, it will seriously behoove you to get well acquainted with vector representations and vector operations. So much of modern computer science is driven by linear algebra. And we're talking about in a number of different ways. Graphics, anything that's graphically represented is usually done in the form of matrices, but so much about what's happening in machine learning and data science is also something that happens with a lot of matrices. In fact, if you ever wondered what the term a tensor was from TensorFlow, it relates to linear algebra. And tensors are effectively abstract matrices that you do operations on. So the very name pulls from linear algebra. You have credits you need to take in math. Use that for linear algebra. By far, one of the most important maths you can have if you are serious about pursuing a software engineering position in fields that are very relevant in today's environment. Okay, let's take a look, a example, and actually map this to an example in terms of how we might represent our fractional binary number as a bit sequence. So here, again, we've added some notation here. Now we have a binary point. We have the left-hand side and the right-hand side of our binary points here. And this sub2 lets us now know what the base is. So this is a base 2 value. If I want to represent that in the form that maps to the sigma summation, I can take each of the positions inside of my bit vector and express them as so. So here, I can take this most significant value of 1. And so here would be my 1's place, my 2's place, my 4's place. So that's 2 to the power of 2. So I would take 1 times 2 to the power of 2. Then I would add that to the next term in my sequence, which is going to be 0 times 2 to the power of 1. Then I would add that to the next term of the sequence. It's going to be here, my least significant bit in front of my binary point, to the left of my binary point. And that's going to be 1 times 2 to the power of 0. Now I'm still going to do my sigma summation, but now I'm going to cross over into a negative exponent value. One of the beautiful things about having negative exponents is that they represent now the equivalent of having or quartering or whatever, right? So it gives us that decimal place that's on the right, or binary point in this case to the right. So here, I'll go ahead and then I have a 1 value here. So we'll multiply that by 2 to the power of -1. And then finally, we'll do the same thing for that next position. So if I want to then show you the actual evaluation, that's the same after we apply the multiplicative property to these exponents would be 4 plus 0 plus 1 plus 1/2 plus 1/4. So when we add that up, that is the binary representation of 5 3/4. Very simple example, but we've just done something very prolific. We just illustrated how we can take an arbitrary fractional value and map it into a bit vector. And so this is what's going to allow us to start mapping our floating point values, this concept here. So you can see this is an extension of the way we would normally do almost our integer-based counting, but it allows us now to start doing our summations where we actually have a inflection points on our radix point value. Okay, so shifting the binary point one position to the left has the effect of dividing the number by 2. So that's, again, let me map an analog to the maths you've had in decimal representation. Just like shifting a point to the left or the right is the equivalent of increasing something by a magnitude of 10 either way, right? So you make one go to 110, or you make 1 go to 10 just by shifting that point. So similar concept on how we shift those points and the effect it has on the binary representation. Which again is why we use this multiplicative property of 2 to the power of k in our representation. So again, if we just want to look at this and prove this conceptually, let's look at this example. We saw that on 101.11, that translated into 5 3/4. If I were to simply shift to my binary point by 1, we can see it's going to have the effect of having that. And we can actually test that by seeing how that binary sequence changes on a per bit level. So now look, it would be the equivalent of having a 2 plus 0 plus quarter, plus half plus quarter plus eighth, which if we sum that together would be the equivalent of 2 7/8, which is half of our 5 3/4. And again, shifting the binary point one position to the right has the effect of multiplying the number by 2. Again, an analog to what we should already be familiar with. And again, we can see if we actually do the math, visually inspect it, this holds true in the example we've already illustrated. So in this instance, we started with 5 3/4. We shift our point by 1. We then retranslate it into the set of integers that we can sum to evaluate what its representation is. And we see 8 plus 2 plus 1 plus half is 11 1/2. And so here is just a table, and this table is given to us in the book as well, that just shows our binary representation and then what our value would be in terms of how we might want to think of it, 0 over 2, 1 over 4, 2 over 8. Just notice your denominator here is based off of the maximum number of combinations you can create that's on the right side of your binary point. And then the numerator is the sum of values that make that up. So this is just a quick representation of what the ratios are between it, right? One integer, a denominator over a numerator. And then we can also show the decimal representation of that as well. So again, you already know how to map these concepts. This is normal math. You could parse these the same way you would. This is all in base 10. But just highlights how we can translate between our radix point value and then our fractional values here. And of course, the important concept is you can see how we can start representing a lot of different decimal values or fractional values that are to the right of our binary. And so, as I already said it, fractional values are inherently approximations. So they're lossy, they're inexact. That's true in decimal notation. That's true in binary notation. Some examples that I actually like to give to illustrate that this is a deficiency, not just in our binary representation, but our decimal representation, is that we don't actually have a value that means 1/3 in decimal, right? We have to just represent it as 0.3333. And at some point, we just say, yes, it's just that many points, like indefinitely. Now, interesting enough, if we used a base 12 system, we could represent 0.3 as something that is not an approximation. So actually, the choice of your bases actually determines whether a value can be represented as a floating point value or not. So there are some values that we can represent as a kind of discrete countable set of digits for a fractional value in one base and not in another. This is an important concept to know because this is why you might have a value that you can represent in decimal notation, but then when you save it and look it up, it becomes a different value after you do an operation on it, because it might translate into the binary equivalent, which doesn't have a actual defined representation, and then it becomes an approximation. There's already an approximation, but then it gets lossy and loses some data, and then it gets remapped into a new interpretation. So for instance, in this example, clearly 1/3, 5/7 is another one that doesn't quite work well in base 10. Whereas in binary, we can only represent numbers that can be written in the form of, right, x times 2 to the power of y. Any other values are going to end up being approximated. So, and then further examples, like 1/5 can be represented exactly as a fractional decimal of 0.2. However, as a fractional binary number, we cannot represent it equally, and instead that has to be approximate. Again, just a motivating concept that things that we think are well-defined because we're in base 10, we lose that interpretation of when it actually gets translated into a binary representation and then translated back into a decimal representation. Because remember, that's always happening. And that also why we never do equality on floating point values. Okay, so let's talk about why IEEE floating point representation is the standard that's used even today in terms of representing our fractional values, our floating point values. So the positional notation that's in the previous approach is not efficient for representing very large numbers. For example, the representation of, and then here we have 5 to 2 to the power of 100 would consist of bit patterns that would be 101 followed by 100 zeros. Right? So what we saw previously is a good way of learning about how floating point values can be represented, but there's a better way to encode them that compresses the number of bits we need for representation. That's really going to be the huge affordance that our IEEE floating point representation is going to give us. So this efficiency becomes more pronounced when dealing with either extremely large numbers, but also extremely small numbers, right? So think about it this way. If we want to grow a number to be very large, we're putting the bit pattern to the left of the binary point. But if we want to grow a value to be very infinitesimal, then we got to grow the binary sequence very far down the right binary point, right? And so if you're looking for precision inside of your binary representation for your fractional value, you want as many bits to either the right or the left, depending on whether you want a very big value or whether you want a very little value, but a very little value that's very precise in terms of how close it is to an infinitesimal unit, then the current approach we looked at doesn't scale well, right? So the solution here to address this limitation is to introduce this floating point format, which will allow us to get these very large or close to zero values. And what we're going to see by this, there's some interesting consequences with this standard. We'll actually see a visualization of how this works. So this format is going to save us memory, though, And it's going to offer us, obviously, a broader range of values. And so also, it's important because this is the standard method for encoding real numbers as a combination of a sign bit, an exponent field, and a fractional field. So these are going to be the three pieces of data we're going to use to be able to encode our values. So now we're going to redefine how we're going to represent our floating point values based off of this new IEEE function. So notice here, we're going to have -1 to the power of s. And so s is going to be the sign s to determine whether the number is negative, s is 1, or positive, which is 0. So this is where the interpretation of the sign bit for the numeric value is 0 handled by our special case. So now this allows us to have negative real values or positive, right? In the way we just saw, we didn't, with the prior definition, we were using unsigned values. Then we're going to have our significand, which can also be called your mantissa, which is going to be our m value. That's going to be our fractional binary value that can have a range between 1 to 2. And then we're going to multiply that by 2 to the power of our exponent, which is going to be the value of a power of 2. And so notice most of our binary sequencing then will allow us to be able to really translate into this domain here. So let's take a better look at what that actually represents. So in a numerical form, given the IEEE floating point form here, we can see that our most significant bit then here is going to be our sign bit. So that is an analog to how we determine the sign bit on integral data. Then here, typically we'll have our exponent field, which is going to encode our E, right? And then here, we're going to have our fractional field, which is going to encode our M, which is going to be this unit here. And so typically in single precision, which is 32 bits, and in double precision, which is 64 bits, based off of the ratio of bits dedicated to your sign bit, your exponent, and your fractional sequences is going to be, let's see, you have 1 bit dedicated to your sign bit, you have 8 bits dedicated to your exponent, and you'd have 23 bits dedicated to your, effectively, your fractional value. Whereas if we go to double, we're able to increase the fractional encoding space from 23 bits to 52 bits. That makes such a huge difference. Let's see if we have some examples here. So here are 3 cases of our IEEE floating point binary values, where we can either have our normalized values, we have our denormalized values, and then we have our special values, which would either represent infinity or NaN. So let's start. And so here we can see what determines whether something is considered a normalized value, a denormalized value, or one of these special case values is going to depend on how in the blue, right, where our exponent field, what values they hold. So notice if it's all ones and this is a binary sequence, then that doesn't make any sense. That's not a valid representation. So in those instances, our system would translate that as either an infinity value or not a number value. So your exponent field here has to have a value, at least it has to have at least a 0 value somewhere in there, right? It can't be all ones. Okay, now with that said, we could see that a denormalized value is one where it's all zeros. And if it's anything in between having at least 1 bit as a on bit, as a 1, and at least one bit that is a 0 bit, that's going to be our normalized values. So let's talk a little bit about what it means to be a normalized value or a denormalized value. I think it's pretty obvious what it means to be a nan, not a number, or an infinity value. So our normalized values represent the most common case. So it occurs when the exponent field is neither all zeros or all ones. So in this instance, the exponent field represents a signed integer in biased form, where E will represent our actual exponent of the floating point number. The little e here inside of our equation, E minus bias, is going to be the unsigned integer value stored in the exponent field. And so this bias is going to be a constant value. It's 127 for signed precision or 1023 for double precision. And so that will either give us this range of between minus 126 to 127 in signed precision, or minus 1022 to 1023 in double precision. And then in our fractional field, we can represent a fractional value where our f here, wait, where did our term, do I have? I'll have to add it in here. But for our fractional value, we'll want it to be anything obviously between 0 and 1, right? That's what we mean by fractional. It's less than a whole number. And just a little bit more explanation in terms of why we have a bias in there. The purpose of our bias term is to introduce how to efficiently represent our exponents and create a balanced range of exponents. We're going to see what the biasness does when we actually look at the number range of how our approximations work. But it allows us this efficient exponent representation. So the exponent field determines the magnitude of the number by specifying the power of 2, which is raised, right? So that's like our k term, 2 to the power of k, to efficiently represent both the small and large exponents with a fixed number of bits. So when we talk about having a balanced range by introducing the bias, the exponent field can represent a range of values that include both positive and negative. That's where we have the sign bit. But the bias also shifts the exponent value, making it possible to express small negative exponents as well as large positive exponents. So let's see. Do I have a representation here? So I kind of want to show that. So just as a case here, so we can see what this looks like, suppose that we have the following value. You can see we have our E term, we have our bias term, which is the constant value in a single precision of 127, and our exponent value, which is effectively just our E term plus our bias term. And so then this term here would be encoded as this sequence here. And if we look, this sequence is in the red, which is in our exponent field. And then in terms of our significand, right, that's going to be our blue term here. We would have our M. And so if we look at our formulas here, we have, let's take a look at the formulas on the right-hand side and then map it to the actual example here. So we can actually translate what's happening step by step. So we have our vector, our bit vector that represents our fractional value can be defined as -1 to the power of s. S is our sign bit, times m, which is going to be our fractional value here, times 2 to the power of e, which is going to be the exponent field here, right? So looking at this, I can know what part of my binary sequence goes to each attribute to this formula. Okay, so another way I can define M then, using this formula, is it's the same way as saying, just take this vector field and right shift it by E spaces, by. So if you see, I have this here. You can see I'm effectively going to right shift it by 13 spaces, which is why I have so many zeros here. So does everyone see how I define my fraction from my m? So again, let's jump here. Suppose I have this value, 15,213, right? That is going to be my decimal representation. I can take this decimal representation and convert into this binary sequence here. I can take this binary sequence and represent that in my formula that I gave here. So the equivalent representation is to use my binary point, 1 point, and then I can then define all of these values and multiply it by 2 to the power of 13, right? So does everyone see that this formula here that I have, this topmost formula, is a way of re-expressing this binary sequence to be equivalent to this formula now? Okay, once I have that understanding, I can then define what my M term is. My M term is going to be this part here. The part that is now to the left of my binary point. So again, what we've done here for this representation is take a very big number and we can express it as being a part of what's mapping to the right-hand side of my binary point. But I can multiply it by 2 to a power of something that's bigger, like 2 to the power of 13, right? And that makes sense, right? Analog, just to make sure everyone's on the same page, because lots of blank faces. If I take 1.01 and multiply it by 10 to the power of 100, that's going to produce a really big term, right? And so, or I could take 1.23456 times 10 to the power of 10, and it's still going to create a big term. That's the concept we're doing. This is effectively using scientific notation to encapsulate very big values or potentially very small values, depending on whether the sign bit on my exponent is positive or negative. So I take the unsigned value, the non-fractional value, I translate it into this form. And so now I can say, okay, I can reproduce that by multiplying it by 2 to the power of 13. So if I do that, then I can then fill this space here. So this, my fractional is then going to be the value that we have here. And if we count the number of zeros, it's going to be 2 to the power of 13. That's the actual realization of that. So here you can see my E term is 13, my bias is 127, I get 140, and that's going to give me my exponent term here so that I can encode that. And so my IEEE representation of 15,213 would then be this binary sequence. Does that make sense? Maybe not super obvious initially, but you can see how much more powerful this is using a form of scientific notation to be able to now really represent very small or very large numbers. But also, it's an approximation, right? It is.
What's the purpose of the bias? Why can't you just like store 13 in the red box?
That's a good question. That is a very good question. I have a visualization that's going to illustrate what that bias does for us. And that bias is actually different depending on whether this is single precision or double precision. Recall in single precision, it's 127. What we're going to notice in double precision, it's, what is it? It's 1022 to 1023.
So the bias just like a tolerance value so that things are lost.
Yeah, it's gonna. Yes, it's going to introduce a biasness that's going to allow us to have approximations in places that we're going to want those approximations to occur. Well, let me see if I have a graphic that makes this a little bit more expressive. Let me answer that question when I get to it. I have a slide to answer that. So just so that we can kind of stay on target with what our cases are, let me just kind of roll immediately into my denormalized values. So denormalized values are these instances where my exponent value here is all zeros. And so my exponent value here, denormalized, blah, blah, blah. This case occurs when the exponent field is all zeros. The exponent value can be defined as 1 minus bias, because remember what our bias term was 127. So if we do 1 minus our 127, that should zero everything out. And so the significant value then is just going to be m is equal to whatever our f term is. And remember, our f term is anything between 0 to 1. So again, the purpose of our denormalized values is it's a way to represent our numeric value of 0. In a normalized number, m must always be greater than or equal to 1, making it impossible to represent 0. So the bit pattern for 0 in our IEEE floating point format consists of all zeros, our sign bit as 0, and all zeros in the exponent field. That should be obvious, but it should be also articulated. A weird oddity here is when the sign bit is 1, but all other fields are all zeros. We do have a representation of -0. Consequence of this representation. Okay, so denormalized values also represent values that are very close to 0, right? This is approximations. So they offer gradual underflow, ensuring that the numeric values are evenly spaced near 0. What does that mean? Okay. Remember, the real important thing about floating point numbers is creating definitions for very small units of space between elements. That means we want to be able to represent a number that gets very close to approaching 0, but isn't quite 0. And then our special values. I think this is kind of obvious. Special values is when our exponent value is all ones, then this can be things like undefined numbers, such as if you try to get infinity. Like if we take 1 and divide it by 0, that's going to produce an exponent field that's going to be all ones. So we have our two different values here where we actually show what we can do to go ahead and generate those. Okay, so let's start kind of introducing some of these concepts of visualizations. So really, if we want to think about how we want to think of our normalized versus our denormalized values, we have our center point here at 0, and we can have +0 and -0, whatever. It just lets us know what direction we're approaching from 0, right? So think of it almost as limits in calculus. So those numbers that are approaching 0, that are going to be very close to 0, are going to represent our denormalized form. That's where our exponent field is all zeros. Now, our fractional field might not be all zeros. So that's an encoding value that's going to put us next to zeros, but give us a lot of bit patterns that we can designate as close to 0 spaces that are distinguished from one another, that are discernible against one another. So here we'll have a tight mapping of these denormalized spaces. And then as we approach further from 0, we actually get less binary sequences. So we actually get holes inside of what we can represent, but that's going to represent our normalized space. Because at this point, we're starting to multiply our significand by 2 to the power of some exponent, right? And so we're going to see that's going to result in holes, real approximations. I mean, it's the same approximations, but it's going to be very evident on the amount of gaps you then get, depending on your how big or little the number is you're trying to represent. Okay, let's see here. We have an example, but let me show you first. We'll walk through this example in a moment, but I did want to show you some examples while it's on. Okay, this is just, I was looking for the first visualization to really highlight this. Imagine if we tried to do a number line of a 6-bit representation. And next class, I kind of want to walk through these slides and motivate it more, but this will actually give you something to map conceptually. This is a number line of everything we can represent if we limit ourselves to a 6-bit encoding using the IEEE format. So that means 1 bit for the sign bit. That means 3 bits for our exponent field and 2 bits for our fractional field. Notice on here, we get tons of values that populate next to our 0. But notice our encodable space are only these purple triangles. So there are literal gaps on the number line that just can't be expressed. That's why that bias term is introduced, to allow the behavior to be able to bias our terms in certain ways. And so we can see here that this would not be a great representation if you needed something like minus 11, right? You just can't do that. You just jump from like minus 10 to like maybe minus 12.5. And again, we'll motivate this a little bit more. We're out of time right now. But you could see this is a very powerful way of being able to use a finite number of bits to represent these really small and large values. And we'll examine it a little bit more. Maybe we'll play around with the little source code next lecture. And then we'll be done with this chapter. And we'll move on to another chapter. Yeah, all labs, just to answer the question on the chat. Yes, all labs you should use the web terminal for, because there'll be special services that you can use that are pre-installed for you to do your labs.